Okay, today I just want to go over a few more solubility product practice questions. So we're going to be focusing on given KSP, find the molar solubility, but also um, talk about common ion effect and how to do calculations involving the common ion effect. And then again, if we do end up calculating molar solubility of a compound, whether in the presence of a common ion or just in distilled water, what we can, the type of calculation we can do with the value of the molar solubility of a compound. So just want to do a couple questions involving that just as we're gearing up for our Unit 4 test. All right, so let's go to the tape. All right. All right, so here we have, it says lead 2 iodine has a solubility product, a KSP of 2.3 times 10 to the negative 16. So remember, that value is telling us not very soluble, obviously. And based on solubility rules, we wouldn't expect lead 2 iodide to be very soluble. All right, so we have the KSP for this compound. And the first question is, what is the molar solubility of lead iodide? So we're given this KSP, and we want the molar solubility in pure water, so we can use our KSP shortcut. Now, this ionic compound has a 1-to-2 ratio of ion to ion, so that means we use this shortcut, 4x cubed. So we'll just plug in our KSP value into there, and we'll say 2.3 times 10 to the negative 16 equals 4 times x cubed, and we'll solve for x, and x will be our molar solubility. All right. So what we would do is take this, divide by 4 first, and then we would take the cubed root, and that'll give us our molar solubility. Now, a couple things to really understand. Remember, whenever you're reporting a K value, they don't come with units, right? All we really care about for a K value, and it doesn't matter if it's KSP, KP, KC, whatever, KA, KB, we just care about how small is this number or how big this number is, right? That's really what we're talking about. But the units don't really matter to us when it's the K value. But when we calculate molar solubility, we need to include units. And you could say capital M for molarity over here, but you really should say moles per liter, because that's going to lead you into how can you use this number in a calculation. Just understand, if we were asked how many grams of a salt we can dissolve in 1 liter, what we would do for this is we would multiply 1 liter times this would give us moles, and then all we would have to do is calculate the molar mass. So understand, molar solubility is a conversion factor. It can be used to say this many moles per 1 liter, or you could say 1 liter over that many moles. So this is our conversion factor to either convert from volume of a solution to moles of solute, or to convert from moles of solute to volume of a solution. All right, and we're going to do some sample calculations with that in a second. But now we're going to look at the common ion effect. Okay, so anyway, we have KSP equals 4x cubed, and we got our answer. This is how many moles per liter we'll have of this compound in a saturated solution at whatever temperature this is going on. All right. So part B, they ask us for the molar solubility of lead iodide. So the same question from up here, but notice it's not in pure water. We're in a solution of potassium iodide. And so assuming the temperature hasn't changed, we still know the KSP that was given to us at the top. We know the KSP of lead iodide. So we know the equilibrium position of this reaction, right? So the deal is we have to recognize that we're dissolving this ionic compound in the presence of a common ion. So this is potassium ions and iodide ions, and the common ion in question here is I minus. Okay, so we already have I minus in solution. Up here in part A, we didn't have any I minus. So we were just dissolving in pure water. And remember how we get our shortcuts. We made a Rice chart, we get our equilibrium concentrations in terms of X, we plug them into the expression, and we solve for X. And whenever you have a 1-to-2 ratio, this is going to be what you get if you're set up your Rice chart and it's dissolving in pure water. But in the presence of a common ion, like here, we can't use that shortcut. So the KSP, that value is still that number, okay? But now we can't say it equals 4x cubed. We got to figure out what the expression is it's going to be equal to, all right? So what we're going to do is set up our Rice chart. So this is the equilibrium we're talking about. Before any dissolves, we don't have any lead, but we do have I minus, and we know we have 0.005 molar I minus. So that's the initial concentration of I minus, all right? We're still gonna shift this way to reach equilibrium, so it's gonna be plus X, and notice our coefficient, plus 2X here. And then so at equilibrium, this will be X, and if it wasn't a common ion question, then this would be 2X. But because it's a common ion, this isn't 2X at equilibrium, it's 0.005 plus 2X, all right? So we would plug that into our KSP expression. So remember what the KSP expression would be for this reaction. It would be the concentration of lead, which is X, times the concentration of I minus squared. So here's the concentration of I minus, we plug it in, but we have to remember to square it because of our coefficient there, all right? So what we're gonna do is solve for X, okay? And again, anytime you solve for X in a KSP Rice chart setup, X is the molar solubility of the compound, okay? So in this situation, X would also be equal to the molarity of Pb2 plus, but also understand that that's the molar solubility of the compound because the ratio is 1 to 1. One lead ion to one lead to iodide, right? But to solve for X, we're gonna make it simple. So again, remember, the value we're plugging in here is this one, 2.3 times 10 to the negative 16. So that will plug in 2.3 times 10 to the negative 16 here. But remember, we're gonna get rid of this 2X because we're gonna 5% rule it. The amount that 2X is equal to is so small compared to 0.005 that we can just ignore it. So really what we're gonna say is the KSP value equals X times 0.005 squared, and we're not gonna have the 2X value there. So when we solve for X, we get 9.2 times 10 to the negative 12 moles per liter. So that would be the molar solubility in the presence of a common ion. Now, we should have expected a smaller number than what we had before. So this was the molar solubility in pure water. And remember, the common ion effect states that a compound becomes less soluble when dissolved in the presence of a common ion. So this was the solubility in pure water. So we know the solubility in the presence of a common ion would be less than this number. And it turns out to be significantly less. But for some reason you came out with a number bigger than what you got in part A, then obviously you're wrong. But again, that's moles per liter, all right? All right, so calculating molar solubility in pure water, calculating molar solubility in the presence of a common ion. Now we're gonna calculate molar solubility in the presence of a common ion again, but then we're gonna use that molar solubility to calculate a number. So we wanna know how many grams we can dissolve, how many grams of this salt, lead iodide, we can dissolve in 500 milliliters of solution. So remember, that's 0.5 liters, all right? And so in order to do that, we need to calculate the molar solubility, but notice we're in the presence of a common ion again. We have 0.001 molar lead nitrate. So our common ion in this question is the lead 2 plus. So we're still doing the same equilibrium. It's the lead to iodide dissolving, and the KSP is still this number up here, okay? So that's what we would be plugging in here. But since we're in the presence of a common ion, we'll make our Rice chart again. And we'll say 0.001 and 0 and plus X and plus 2X, okay? But at equilibrium, this will be 0.001 plus X and this will be 2X, okay? So we plug these into the expression. So we got the iodine concentration, which is 2X, but we got to square it because of that coefficient. And that is the lead concentration. We're going to 5% rule. We're going to get rid of that X because we're assuming that X is so small compared to that number. Even though that number's small, this number's going to be a lot smaller. We can just get rid of it. And so we have KSP equals 0.001 times 4X squared. And if we solve for the molar solubility, boom, we got it. Now that doesn't answer our question. That's just the molar solubility of this compound in this solution. That's how many moles per liter it will take to saturate. So the question is, if that's the molarity when it's saturated, how many grams of this can I dissolve? So what we would do is, All right. So what we would do is, okay, so now what we are going to do with the molar solubility is convert volume to grams of our solute. So volume of solution to grams of our solute. So the way we're going to do that is this is our conversion factor from liters to moles. So we can say this many moles over 1 liter, but for this question, we're going to say 1 liter over that many moles. Or sorry, no, we're going to say this many moles over 1 liter, right? So what we're going to do is take our volume in liters, so 0.5 liters, and then we're going to multiply by the molar solubility. That'll cancel out liters, and that'll give us moles of lead iodide, and then we multiply by the molar mass. So the setup would look like, whoops, where is it? This, all right? So we take our 0.5 liters, multiply by the molar solubility we just calculated, liters cancel out, that'll give us moles of the lead iodide. We'd have to calculate the molar mass, 2 iodines and 1 lead, so it comes out to be 461 grams per mole. And if we multiply by that, moles will cancel out, and that'll give us grams. And again, it's not soluble, and it's even less soluble in the presence of a common ion, so it's going to be a very small amount. But about 5.5 times 10 to the negative 5 grams, or 0.055 milligrams, okay? But this is the type of calculation you need to be able to do using your molar solubility, okay? So, yep, all right. That's, I just wanted to show you a couple practice problems with molar solubility in common ion. So hopefully that helps you prep for the test.